Hey everybody, good morning. How are you? It's Sunday, which means that it's time for our introduction into statistical learning class. I hope that you're doing well. I'm doing pretty good. I've gotten a nice start to my morning. So I'm looking forward to spending next bit of time with you. Honestly, it's probably going to be a couple of hours. We haven't gone anything less than like 2 hours and 15 minutes, I think is as short as we went. And we've gone almost to 3 hours. So I don't know how long we're going to go, but we're going to have some fun today. I think we got some pretty interesting materials to go over, and we'll just kind of see where the class ends up. I've really been enjoying the interaction that we've had. The people in the chat have been really great about being constant participants and giving their views and things like that. That's really good stuff. That way we can learn from each other. I learned a little bit from you, and that's good. And, I think it just adds to the overall feeling of growth here, right? Because we should really be all proud of ourselves, right? I mean, this is the 5th session, and we are on chapter 7. So we are past the halfway point, right? We only, this and 3 more sessions, and we're done. And then chapter 7 is this one and 3 more chapters, right? There's 7 we'll cover today, and then 8, 9, and 10. So we are making some great progress on this book. Really proud of all of you guys. I know that a few of you have been here every single class, and I know that's even, and some of those people have been here for the entire time, which, like, for each class, which is a lot, because like I said, we go at least 2 hours. So good for you guys. And if you can't do that, that's okay. You can watch the replays on YouTube. You can come later in the session. Maybe you want to come like in the 2nd hour, or maybe even in the 3rd hour. Sometimes we are going long. So yeah, so really excited to see where we end up today. I'm already seeing people across all the chats, which is fantastic. I guess I haven't actually seen anybody on the Instagram chat, but let me make sure I have that up. But yeah, Instagram is being a little bit shy today. So what I've also done for Instagram, guys, is I have pinned a message in Instagram that will take you to the YouTube view, the widescreen view, because for Sunday's classes, I think the widescreen just works a little better. Maybe that's something that I'll adjust sometime in the future, but for the purposes of today, I would recommend that you switch over to YouTube to be able to see everything, because I do share a lot on the screen. I have slides that I prepare. We do code and things along those lines, okay? And actually, speaking of slides, I have a lot of slides for us to go through the day. Lots and lots of slides. So I kind of want to get started as soon as we can. But yeah, looking forward to it. I have a feeling we're going to be at least 2 hours, maybe a little longer. We'll see. We'll see. I have a lot of slides to go through. A lot of interesting concepts. But at the same time, I have a feeling that today is really kind of like a visual day, right? I think that some of the stuff that we're going to be talking about is very visual. So it's going to be interesting to see how the class develops and kind of how our conversation goes, because I think there are a lot of things that are going to kind of make you think in a different way, or maybe just more in a visual way than we have so far, right? So before we jump into the slides, I do want to get started as soon as we can, but I do want to acknowledge the chat. I'm seeing a few people in the chat already, a lot of our regulars, which is fantastic. So starting off, Rohan, good morning. You're reclaiming your place at the very top. So Rohan, glad to see that you're here. Hope that you're doing well out there in India. I know, Rohan, you've been one of the people who stays for the whole class, so good for you, my friend. That's awesome. Joseph, one of our great moderators, says, "Happy Sunday, everyone! Excited about today's class." Yeah, Joseph, thanks for that. Good to see you, and I'm excited too. Today is maybe where we start talking a little bit more about the creative side of data science. So let's see where we end up today. Sarvesh, nice to see you. Sarvesh, I know you've been attending the classes quite a bit. Hello all, Sarvesh here from Mumbai, India. Welcome, Sarvesh. Hope you're well. I know it's late in India, so thanks for staying up with us. Rex, our moderator on Twitch. You can see the little sword icon that indicates that Rex is one of our moderators. I don't know why it doesn't do that for YouTube, but good day, everyone. Rex from New York City. Hope you're doing well out there in New York City, Rex. I think it must be beautiful out there right now, right? I mean, I heard they have some really good weather. Michael's another one of our consistent Sunday participants. Happy Sunday, Dennis, and everyone. Hope everyone is good. Hope everyone is doing just fine. I'm speaking for myself. I'm doing great. So thank you so much. I was working on some of my hobbies yesterday afternoon. You got to have some hobbies away from data science, away from computers, right? So I was working on some hobbies, having some fun yesterday afternoon. So I hope you're doing well too, Michael. Leo says, good morning, chat. Good morning, Dennis. Leo, how you doing? Leo's also a great participant, not just here on our chats, but also on Discord. So if you want to check us out on Discord, I've also included the links in the chat. Really good community that we're building there. We are like over 120 people now or something, which is mind-blowing to me. Mind-blowing to me. Where did y'all people come from? Rahul, how are you, my friend? Hello, Dennis and Patrick. Happy to be here again. How are you guys doing? Doing well, Rahul. Thanks for asking. Yeah, I know you've been consistently attending the Sunday classes, so I hope you're getting a lot out of this. Lakshmi, good to see you. Good morning, Dennis. Morning, everyone. Hope you're doing well, Lakshmi. I know you're back again from last week. I think you were here the entire class last week, so good for you. Hello, Dennis. Rahul says, hello, Dennis. Happy to be here again. How are you doing? Yeah, I'm doing well. Thanks so much for asking. Doing well. Really excited about today's classes. I put together the materials 2 days ago, and I think it's going to be a good class. Manoj, good to see you again. I know you've been attending a lot of the streams this week. Good morning, Dennis and all from Bangalore, Hesaragata, India. Hesaragata. I hope I pronounced that right. Well, good. Welcome, Manoj. I hope you're able to enjoy today's class. And I love the feedback from all of you. So if there's something in the class that you didn't understand, or something I can improve on, or something else that I could be doing better, just let me know. But I think the class conversations having a great two-way street where we can kind of talk to each other and participate, and just kind of, have a good time talking back and forth while we're learning at the same time, right? Okay, so just as a final reminder for anybody that's still on Instagram, you can find the pinned comment that I wrote that will take you directly to the YouTube view. That's going to give you the wider screen view, a little bit more convenient for you to see. But otherwise, I'm not seeing any more intros in the chat, so I'm ready to get started. So let's do this. I think this is going to be fun. Let me bring up my monitors. All right. So this chapter is called Moving Beyond Linearity. Why do we need to talk about moving beyond linearity? So I want to go into the next slide, and let's kind of set the tone for what exactly it is that we're focusing on, right? And so far, everything we've talked about, for the most part, right, has been linear regression, right? So we've basically have covered, two major topics, right? We've covered linear regression, which is a form of modeling, right? And then we've also covered the features, right? How do you select features? So those are like the two meta concepts that we've covered. Selecting the features is kind of independent of anything else you do, right? You're kind of always going to be needing to select features. But linear regression is kind of a unique model. And the problem is that it's linear, right? It's assuming that there's a linear relationship somewhere in your data or in some combination of your data. But the reality is that we do not live in a world where everything is linear, right? So in this chapter, Moving Beyond Linearity, we're basically talking about different approaches or different ways for us to work with data that is not linear, because we don't live in a linear world. And in turn, that opens up the possibilities to work with more data and more features from that data. Because maybe there were data sets previously that you didn't work with, right? Or maybe there were some features that you disregarded because there wasn't a relationship there, but now you can find one. So that's kind of what we're going to focus on today, okay? So I want to highlight some of the really good work that's been going on in our Discord. So this here is part of a study from our Discord that was done by Yassine. And I saw that Yassine just came in. Hello, sir, Yassine from Fez, Morocco. Welcome, Yassine. You're just in time. Just in time to see your own work on the screen. So this is a chart that Yassine had brought up on Discord that was looking at the California housing set that we worked on last week, in the same class. So audience participation time, and guys, let's start right away with a question. Can one of you tell me which one of these is the linear relationship? Yeah, so tell me the row and then the number in that row. Which one of these is the linear relationship? I'll give you guys a minute to think about that. Where is the linear relationship here? Tell me the row and then tell me the chart in that row. Top row, bottom row, and then number 1, 2, 3, 4. Yep, thank you, Rex. Rex is pointing out that the Discord link has been pinned. I did that earlier today. And that's on Twitch. What do you guys think? Where's the linear relationship? Okay, so Leo is proposing bottom row, 3 and 4. Top row, first graph from Rahul. Okay. Yassine says closest one to linear regression is the first row, first column. Okay. So we got a couple people pointing to this one here, first row, first column. Anybody else? If this is your first time joining or you're shy about participating, you can just agree with another person. You don't have to, give a long answer. Just if you want to agree with somebody, you can also do that. Anybody else? So later on, we're going to come back to this chart. But I would argue that there is potentially no linear relationships here, right? It's possible that there is no linear model to be had here. Are there other models? Maybe. Yeah. But I would argue that there's no linear relationship here. And I'm using this to illustrate that this is one of the exercises you should be going through during your feature selection. You should be plotting out some of your data and saying, okay, well, what does it look like? And that's why I'm really saying that, today is going to be really, really visual, right? Where you kind of have to develop an eye for these things and maybe be creative in a little way, in a different way, right? So we're going to come back to this, but keep that in mind, right? That don't try to force a linear relationship if there really isn't something there, right? Because if we go to some of the further slides, something like this, right? That's clearly a linear relationship, right? Not just because the black line is there, but if you just look at the scatter plot, right, at the red points, right, there clearly is a linear relationship, right? It has a very defined range and a defined direction for that linear model, right? I think we can agree on that. I mean, we've seen this chart before in a couple of the previous classes, right? So again, the authors acknowledge, hey, we don't live in a linear world, right? So they're giving us a series of nonlinear approaches. So they present us with polynomial regression, step functions, and then splines. And then we're going to talk about like two subsets of splines. There's regression splines and then there's smoothing splines. And then the authors close out with local regression and generalized additive models. So I'm probably going to make this point a couple times to you during this class. But one of the things I also want you guys to keep in mind is I am very careful about the vocabulary that I use, especially, and I'm encouraging you to do the same, because regression is a method. It's a type of model. Linear regression is another, it's like a subset of that modeling. Polynomial regression is another form of that model. Ridge regression is another form of that model, right? So I want you to think about this because, and I say this because I see a lot of people who kind of just say, oh, it's linear regression. Well, it's not. It's regression. It just happens to have a linear relationship. So I want you to think about it as the umbrella is regression. And then linear, polynomial, stepwise regression, that's describing the relationships in the data. Okay? And I'm also saying this because this is kind of like that mindset and the vocabulary that kind of puts a little extra polish on your approach to data science, in your modeling, in your resume, and even in your interviews, right? It's regression methods. We've been studying linear regression. We're going to go on to study polynomial regression, or stepwise, or spline regression, right? And also, you'll see that in some of your classes, right? You shouldn't really have a linear regression class, but you're probably going to have a regression methods class if you look at most curriculums out there. For probably not the undergrad, but certainly at the grad level, right? So I kind of want to use that to set the tone, also, so you guys understand that the vocabulary is a little bit more important in this chapter. Okay. But it's something you'll develop over time. But just keep that in mind as we go forward, because I'm very careful about that. Okay, so I use, maybe this is a little bit out of sequence. I should have had this chart first. But again, I'm using this to show you guys, right? This is clearly a linear relationship, right? What about this? What do you guys think about the chart on the left? It's not a line, right? But you're still using an X and Y. You're still using a formula, right? An algorithm to come up with this line, right? So that's an example of an X squared regression, right? I mean, that's essentially your first polynomial regression. And just so we're all clear on that, right? When we're referring to polynomials, we're referring to like a square or a cube or something of a particular X value, right? Of your independent variable. So this is kind of like your first, and kind of like your most basic model for polynomial regression, X squared. So instead of y equals mx plus b, as we've seen before, it's y equals mx squared plus b. That's all it is. That's all we're talking about in polynomial regression. So knowing that, what can you tell me about the graph here on the right? I'll give you guys a minute to think about that. Just give me your explanation. What is your take on the graph here on the right? Rahul says, aha, I knew it was a trick question. That's right, Rahul. You guys should know me by now. You guys know I like to, throw in a couple things to make you think. But what do you guys think about the right chart? What's the right chart? Hey, Patrick, good to see you. Patrick is also one of our moderators. So, guys, if you see Patrick, Rex, or Joseph's, give them a shout out. If you see them here on the Discord, they really help me out with the moderation on YouTube and on Discord and on Twitch. So, thanks to those guys. Give them a shout out when you see them. Sarvesh says should be X cubed. Yep. Anybody else? Anybody else agree with Patrick or Sarvesh, or they want to give a different answer? Maybe this is a trick question. You never know. Got to keep you guys awake. Anybody else? Okay. Manoj says, is it logistic regression? Okay. So Manoj is asking an interesting question there. Is it logistic regression? If anybody in the chat wants to contribute to that answer, let me know. Rex says, Patrick and Joseph, thank you both for your help in Inside Data Science. Yeah, thanks for the shout out there, Rex. I really appreciate all three of them and their modding capabilities. Leo says, nonlinear regression. Yeah, you're right, Leo. It's not a line, right? It's not x equals y, right? Or excuse me, I said that backwards. Y equals x, right? Sarvesh says, or it could be x to the n with n being odd. Okay. Yassine says, agree with Patrick. Yep. Okay. So, good answers here. I love the chat. Let's tackle Manoj's question. Is it logistic regression? This is a nice little Manoj. I'm really glad you asked this question because we're kind of like doing a little bit of review, right? Ashish on Instagram says, "What's the question?" Ashish, I'm showing some diagrams up on the screen, and I'm asking what you think the right diagram is. Ashish, I see that you're on Instagram. Feel free to switch over to YouTube where you can see the diagrams a little bit better, or you can stay on Instagram. Appreciate your support. But just letting you know that on YouTube, it'll be easier to see the rest of the class. K Asabre says x cubed. Okay. All right, yeah. So let's leave that for a little bit. Let's ask a second question. Let's help Manoj out here, right? Is it logistic regression? If you know logistic regression, right, from our previous classes or maybe your own study, there's something in here that would prevent this from being logistic regression, right? There's kind of a giveaway here. Leo says, yeah, one of the things to find a better relationship between the variables. Yeah, Leo, yeah. That basically sums up a lot of the items we're going to cover today, right? That's what I mean about the visual side, the creative side. So we're going to get a little bit more into that, Leo. Yassine says, isn't the logistic regression considered a linear method? Yeah, you could say that. But there's another giveaway here. See, Manoj is not fully incorrect, right? His instincts are good because he knows that there is a curve to the logistic regression model, at least to the final answer, right? Because remember, logistic regression, the final answer you get in logistic regression, it's I think it's considered like a log, right? It's a log of your regression value, right? Ah, okay, Ashish and Patrick are hitting on something very key. Rahul's got it too, yeah, right? logistic regression, we know has a range, right? Logistic regression is range bound because it's basically a proportion, a probability, right? I shouldn't say proportion, it's a probability, right? So this can't be logistic regression because we're modeling negative values. So Manoj, I love the question because it gives us an opportunity to review, but it also gives us an opportunity to kind of draw that distinction between the graphs that we see. Because on a graph basis, it is tempting to say, yeah, this looks like logistic regression. I totally see, why you said that answer. I get it, right? But we also know that logistic regression is range bound, as Patrick and Rahul, figured it out, right? That this can't be it because it's 0 and 1. It's between 0 and 1 for the values, right? So Sarvesh says, agree with Patrick. She says sigmoid curve does that job. Yep, that's true. That is called a sigmoid curve. And Leo says the binary aspect of logistic regression. Yeah, right. The binary aspect is still referring to the 0 and 1 range. So Manoj, I love that question, but I hope you understand. I hope that clears it up for you. Manoj says yes, thank you. Okay, cool. All right. So yeah, so most of you landed on it correctly, right? This is x cubed. But I'm really just showing you this, to Leo's earlier point, that it's about understanding the different relationships that data can have, the different relationships between x and y. And when we say the different relationships between x and y, we're really saying the different relationships between your independent variables, what you're using to predict, and your target variable, what you want to predict, right? And that's kind of how the world works, right? There could be any number of features that have a variety of relationships to whatever it is that you're trying to predict. Because again, we just said the world is not linear. The world is not always y equals x, right? So that's kind of like, where we're going with this. And why today I just feel so much more visual, right? Because these patterns are the way I was taught. And the reason, and by the way, I should have started with that, sorry. But the reason I did this chart is because I don't think the authors did a good enough job of kind of walking you through these charts. But when I did my graduate studies, there was at my school, I went to Penn State, and at my school there's a dedicated regression methods course. You do nothing but regression methods for an entire semester. And this is one of the things, this is how I was taught, where they just show you the different graphs. Just, what does it look like when you're talking about x squared? What does it look like when you're talking about x cubed? Because then it's up to you to remember that. And the next time, you're looking at different plots, you can say, oh, wait a minute, I kind of recognize that relationship. I kind of recognize those plots, right? I mean, that's kind of the essence of polynomial regression, fitting your data to like the different potential relationships. Okay? All right, let's see what the next slide holds for us. So here, I'm showing even more of the different graphs, right? These are additional x cubed graphs. But I'm using this to illustrate how you could also be adding additional modifications, right? So here it's x cubed minus x, here it's just x cubed, and here it's x cubed plus x. So you can use additional factors to help you shape your line. Because remember, at the end of the day, you're just trying to pass your graph through the existing data, through your ground truths. That's kind of like that's kind of like what you're trying to model, right? How can I pass a shape through my data with the least amount of errors? Right? That's kind of what we've been doing. It's just that instead of straight lines, now we're dealing with different lines. Right? I mean, I think you guys can see that. If we were to go back to our previous chart, right? You could say that about this chart, right? What is the path I could take through my points, through my ground truths, and have the least amount of errors? That's what we've been doing, right? Because as we know, these black lines represent your errors. And from there, you can get all the metrics we've been working with, RSS, MSE, R squared, right? So when we look at a chart like this, where am I? So when we look at a chart like this, it's really no different. It's just that it's not a linear equation anymore, right? Life is not a straight line. The world is not straight lines. All right? So let's revisit this. So coming back to my earlier point about vocabulary, right? Previously, I asked you which one is their linear relationship, right? So now I want you to take a look at this chart again. And I'm asking you, where is the regression relationship? I'll give you guys a moment to think about that because we just went over a couple of new charts, right? A couple of new patterns. What do you guys think? Okay, Leo says 3 and 4 again. I assume you mean the second row, right? The 3 and 4 in the second row, Leo. Okay, yeah. So Leo says second row, 3 and 4. Anybody else? Give you guys another 30 seconds here. Okay. So Patrick says agree with Leo and maybe 1-1. Okay, so Leo and Patrick, tell me the relationship that you see. Like, what is the pattern that you see there? Because remember, we're kind of like doing pattern matching at this point, right? I just showed you what the x cube, or excuse me, the x squared looks like, what x cube looks like. You can modify those with additional parameters, right? What do you guys see there? Yassine says, agree with Leo plus first row, first column. Okay, Yassine. So while Patrick and Leo think about 3 and 4 in the second row, Yassine, tell me what you see in 1-1 in first row, first column. What do you see there? Hey, DevEV, thanks for joining. I see you're on Instagram. Feel free to join us on YouTube if you want to see the widescreen view. It's a little bit easier to see the charts, okay? But thanks for joining us. But what do you think, Yassine? What's catching your eye about 1-1? And same question to Patrick and Leo. What are you applying there? What are you applying there to second row, 3 and 4? Let me know the pattern that you're catching, right? You gave me your answer. Now I'm asking for your rationale. Or anybody else who wants to participate, feel free to give an answer or feel free to agree with one of these guys. So Patrick says, I'm seeing parabolas. maybe an x to the fifth in the 3 and 4 on the bottom row. Okay. Okay, cool. I'm loving the x to the fifth contribution. Okay. Leo says the curvature, I'd say it shows a more complex relationship between the data. Okay. Manoj says no linearity. Now, Manoj, are you saying that across the board? And remember, we're not necessarily looking for linear relationships, right? We just went over some new charts that kind of should open up besides a straight line. I agree with you that there was no linearity when I first presented this to you. But I've shown you, give me just a second. But I've shown you at least 2 new patterns, right? So as Leo and Patrick pointed out, they see a parabola. They see an x squared, right? Or there's these where you can modify even further, right? So think about that one, Manoj. See if you want to revise your answer. Okay. So random seed 42, welcome. I don't think I've seen you. 1-1 lock. What the heck is that? Cannot be auto saved. That's weird. Let me save anyway. Oh, that's weird. That's weird. I don't never gotten that message before, but the file is still working. Weird. We'll just go on. So random C42 says 1-1 looks like the positive side of x squared. Okay, yeah. Anybody agree with that? Patrick says I agree with random C42. Yep. Sarvesh says in the plots 1, 1, 1, 2, 2, 3, 2, 4, there's too much spread. I think any regression model would give a poor fit. Oh, okay. Okay, so Sarvesh is basically saying you're all wrong. You're all wrong. There's nothing there. Right? What do you guys think? But I hope you guys are starting to see that this is kind of like the beauty of data science, right? Sarvesh is saying, no, there's nothing here. Patrick and Leo are saying, no, I see a parabola. I see a parabola here. Right? Who was it? 42 said, I see a parabola here, just half of it. Right? So this is part of those discussions, part of that creativity in data science, right? Like, we're basically doing pattern matching here. So the way I match it, the way I see it, may not be the way you see it, right? I mean, who saw that there's a parabola here, or a potential parabola here? I'm being honest, I didn't. But, yeah, I kind of see it now that Patrick and Leo pointed it out, right? So I hope you guys are starting to see that, this conversation and this back and forth is kind of like part of being a data scientist, how you're going to talk things out, how you're going to like think about solutions and kind of work through the different possibilities. This is part of the testing, part of the experimentation, and so on. Okay? So building on that, I'm going to give you my eye. My eye tells me that I really only see one potential for relationship. And that's 1-1. I'm seeing an x cubed here, right? Because I'm seeing a relationship of the scatter plots that gets steep very quickly, right? That's a very steep relationship between x and y, between my independent and my target variable, between my predictor and my target variable. So that's where I thought, because if I look at that and then I look at, let's say something like this here, the x cubed plus x, I kind of see that relationship, right? Now, let's focus on the bottom one. uh, 2, 4, right? Yeah, I kind of see a parabola here. I kind of see a parabola here. But the challenge with the parabola, and even with my answer of the x cubed here, and by the way, whoever said that there's a parabola here is probably not wrong. I mean, I can see a parabola here too, right? But the challenge with a parabola and the modeling in this one is that if we mentally draw a parabola here, what about over here? What about over here? Those basically become errors, right? Those become errors in your model. Same thing here, right? Even if we were to draw an x cubed, you still have quite a few errors to the side, on either side on that, right? So what that tells me is that there's a potential for a model here, but it's probably not going to be a very accurate one. We can visually see that even in the best path, you're going to have plenty of dots, plenty of ground truths that are going to add to your error function, right? To your error metrics. So yeah, I see the parabola here, but probably not a very predictive one. Because you have like this noise over on the sides, for the different ranges or extremes of the latitudes that are going to give you a lot of errors. Because like every dot over here is going to be really, really far from that parabola, right? And that just adds to your error metrics. But these are the things that you should be going through when you're kind of figuring out, one, is there a viable model here? And two, what does that model potentially look like? So those are the things that you kind of need to start thinking about. Here's a third thing to consider. And in this one, I'm going to give you caution before I tell you this one, because this is kind of where you're potentially introducing bias into your models. The third item that you could consider, if you wanted to, is to think of is to add the domain knowledge, right? And we know that this is a housing set, and we know that the target is about the price, or the price or the value of the home, right? So if we're stuck between this one here, 1-1, which has gotten a lot of attention from a lot of people in the chat, versus 2-4, if we wanted to, we could also say, well, wait a minute, this is median income. That's my X, that's my predictor. Does median income have an effect on price on the value of a home, the price of a home? Yeah. Higher income people can afford higher priced homes. This one here, we know it's the longitude. The longitude is being measured against the target. It's being used to predict the target. Is it possible that longitude has an effect on housing price? Maybe, maybe not. But again, that's kind of like my bias, right? You're kind of starting to introduce your bias a little bit there, right? So you kind of want to be careful on that too. But there is like this balance, like this teeter-totter you have to find between, like, does the independent value that I'm singling out even make sense? Median income, yeah, that makes a lot of sense. Longitude, maybe not. Could I transform that to both include latitude and longitude? Maybe some combination of those will help, right? Like maybe, I don't know, maybe like categorical by geographic location inside a city. Maybe you're on a better track there, right? But is longitude alone likely to be a really good predictor of pricing? You're going to get some pushback, right? Your stakeholders are going to tell you, wait a minute, that's kind of a crazy relationship. So think about that also, right? So I hope that helps you guys. Let's see what the chat says. Leo says, I think the next step would be testing and applying polynomial features to see who's closer. Yeah. Yeah, Leo, this is part of the testing, right? You, remember, to a large degree here, what we're still doing is a little bit of feature selection and seeing what those potential relationships are, right? Maybe they're there, maybe they're not. Who knows? Let's find out. So yeah, to some degree, you're kind of narrowing it down and saying, okay, well now I got a couple experiments to run. So yeah, Leo, you're on the right track with that thinking. Okay. Rahul says it would be interesting to see the graph at 2, average occupancy versus target. With the 4 outliers removed, there's a possibility for the regression model. For 2. Yes. Excuse me. That would be interesting. But on a single predictor, though? Or excuse me, on a single value for x? Or it could be that this scale could have been done better, right? The outliers are throwing off the scale. So Rahul, we'd have to take a second look at that. I mean, I like your overall thought pattern. But what this is telling me though is that this one outlier in particular is throwing off the scale, because then look at how many values are between 0 and 200. So my gut tells me that if you remove that outlier or all the outliers, you're going to end up with something like the one right above it. It could still be a noisy data set. The relationship just exists because it's so compact, right? According to the scale. So this is another thing you guys got to consider, right? Do I have valid plots to work from? Maybe I don't, right? So that's something that you guys kind of need to think about also. Do I have a good plot to work from? So here we're being thrown off by the scale. I bet that if we just went 0 to 200, you'd probably end up with something like this, because there's just so many points between those two values. But we'd have to find out, right? When I say that, I'm just presenting a hypothesis. We'd have to vet it out, right? Again, this is all part of the data science process, part of the experimentation you have to do. So I appreciate Rahul's view on this, but that's what my gut's telling me, that it's going to be a noisy data set. And really, a lot of these are noisy, right? I mean, certainly 1, 2 is a very noisy data set. And 3 and 4, down here, they look noisy, but, I can appreciate why Leo and Patrick can see a parabola here. I get it. So I don't think we're walking away just yet with any clear answers, but that's okay. That's part of the process, right? Science doesn't always have clear-cut answers. Algorithms don't always give you clear-cut answers. They give you probability-based answers. So it's okay for us to say, yeah, you know what? We've made some observations. We need to do some experiments. And, we iterate off of the results of those experiments. That's totally valid. Okay? All right. So I hope you guys are still with me. Give me a 1 in the chat, or a 0 if this is making sense or not. Give me a 1 if you're on board with me, because we're about to close out polynomial. All right, so I got some formulas up on the screen. So give me a 1 or a 0 if you're on board with me so far, or if I've lost you, right? And then also on the screen, give me the invalid formula for regression. All right, Michael says he's still with us. It's making sense. Thank you, Michael. Give me a 1 if you're on board. This is all making sense. Give me a 0 if you're maybe a little lost. Either one is okay. All right, it looks like people are on board with this. Good, good. All right, so now considering the formulas on the screen, give me give me the one that's an invalid regression method. Okay, my nose is still with us. Good. Rahul says, I think all the equations shown are valid. Is he right? Does anybody agree with Rahul? Hey, Muddy, welcome. Muddy, I see you're on Instagram. Feel free to switch over to YouTube if you want the widescreen view, okay? Patrick agrees with Rahul. So, Leo, you think it's the first one? Is that right? Leo says there is no linear regression. Okay, so Leo, I'm sorry, just to clarify, I meant just valid overall, not necessarily to the charts we just saw. So I think you might be saying that there is no linear regression in the previous charts, but forget the previous charts. Here I'm just talking in general. What's the invalid equation that's up on the screen? Two and three is a special case of four. Okay. All right, anybody else? There are 10 seconds here. Leo says, I don't know if four is valid. Okay, anybody agree with Leo? Anybody have that same doubt as Leo? Four is a bit weird because of the subscripts. Yeah, but the subscripts like that are common when you're doing, multiple features, right? Mac isn't always the greatest for writing out formulas like this. Okay, so it's possible that the subscripts are throwing you guys off, but I'm really just using it to indicate different features, right? And different weights. So the answer here is that these are all perfectly valid regression approaches, right? And really honing in on number four, what I'm trying to illustrate there is that you can have a combination of all of these, right? You can have some features that are going to be squared, others are going to be cubed, others don't have to be modified at all, right? You can have any number of combinations. So these are all perfectly valid approaches. to regression models. All of these will give you some sort of answer. It's just, it's really more illustrating the creativity that's gonna be required for you to take that, because we know that we can do regression with single values, like our classic y equals mx plus b. But we can also take that one value and square it or cube it, or we can also put it in a chain with other features, right? And have a multi-feature model. That's totally valid too, right? You guys with me on that? All of these are perfectly valid. Are you guys good? Yeah, so that's the last on polynomial regression. Now we're going to talk about step regression or step functions. So with step functions, the best way to explain that is to do it with a chart. And this chart here demonstrates step functions. Both of these charts do. And step functions basically allow you to have different operations against your predictor variable based on the value of a predictor variable. So you can literally see how there are steps here. So here we have a step up, here we have a step down, and it's all based on the range, or excuse me, on the value of your predictor of your x-axis. So here it's showing age versus your salary. So here they're saying that there's a rise at a particular age and there's a significant fall at a particular age. So therefore this fits a stepwise model. Right? That's basically kind of like what we're illustrating here. So when you think of those stepwise, you should be thinking of a regression approach where you're still putting a line through your data, right? You're still finding a path through your data. But now that line has different levels to it based on the value of your predictor. So if we go here, if you got, I'm pulling this straight from the book, obviously 7.4 if you want to look at it. The author is illustrated with these formulas. And wherever you see a C, the authors refer to that as a cut point. So you can think about it as a cut point, as a step, a cutoff, whatever is easier for you. But you can see here that they're saying, these are the values that I want you to use when X is less than this, or when X is between this, or X is, between this on a higher value, right? So that affects what that path through your real truth looks like, right? Because remember, that's all we're doing, right? We're trying to find the path through our ground truths that have the least amount of errors. That's really all that regression is, right? So sometimes it's a stepped path, and those steps are referred to as the cut points. Okay. Michael says, please come again. Michael, give me some more information. Is there something there that's throwing you off? Let me know. Okay. Kabir, welcome. Hope you're well. Kabir, you're on Instagram. Feel free to switch over to YouTube. There should be a pinned comment on Instagram. Okay. So Michael, let me know if there's a particular point that's kind of getting you stuck. But I want all of you guys to think about this bottom question here. Does this remind you of anything in code? I know many of you have have programming experience, right? Most of you know Python. Does this remind you of anything in code? What do you guys think? Okay, so Michael says the definition you gave for step functions. Okay. For my second question about remind anything in code, Rahul says optimize equations with boundary functions. Yeah, Rahul, you're thinking a little bit too much on that one. Think about it a couple levels down. Okay, so Michael says he's having trouble understanding the definition for step functions. Okay, so let me go back because he's probably not the only one. So Michael, let's focus on this graph here. Okay? And this graph is plotting your age versus your salary, right? So the data says that once you're past like 30 years old, there is a significant increase in your income. And once you're past 65 years old, maybe when you're in retirement, there's a decrease in your income. So it's really hard to model that, right? It's really hard to model that with a straight line, certainly, right? With a linear regression, right? Because we already said linear is y equals x. I'm not seeing a whole lot of a polynomial relationship, right? We already know that y equals x squared is a parabola. These ground truth points, these gray points, don't look like a parabola, right? There's also no cubed here, right? Because a cubed is more of a steep line, and that wouldn't fit a lot of the points. So not everything is polynomial, right? Not everything is linear, not everything is polynomial. So sometimes you need to do a second path, and it's called a step path. Because you're going to have these cutoff points that the author refers to, where you need to treat the weights, the coefficients for your x values differently at different steps, or excuse me, for different values of x, for different values of your predictor. So in other words, the coefficient is not static throughout, right? Y equals mx plus b assumes that that coefficient is always static. It never changes. Stepwise says, no, we can change it, and we'll change it based on the value of x. So that m value is going to have different coefficient levels based on your value of x, driven by your value of x. Okay, Michael, let me know if that clears it up for you. Okay, so Patrick says if then else statements. Yassine says switch case. Yeah, that's it. That's exactly right, right? If you look at this next page, doesn't this look exactly like something you would use to write your if statements or if else statements, right? When x is lower than this, and then when x is higher than this, but still lower than this, and when x is right? That's kind of what you're doing. That's kind of what you're doing in a statistical way, right? You're kind of doing that in a statistical way with this formula, with this algorithm. That's basically what the algorithm does. The algorithm helps you find where those cutoff points are, which you can think about as a separate if-else, right? Or as Yassine says, a separate switch case, right? This would be a separate case, right? Your cutoff points are essentially your case statements. But you're not doing that explicitly. You're letting the algorithm do that, right? The algorithm determines what they are, and then the algorithm runs it, right? So I'm not telling you that we're going to write if-else statements. That's not the point here. The point is that, like, again, you guys know I advocate not having to know the math, right? But what you should know is what's happening under the hood, and that's what's happening. Those cutoff points are being determined, and then your coefficient values are being determined as x, right? Because the if in this series is what is the value of x. If x is this, if x is lower than this, if x is higher than this, right? But yeah, but if you guys can see that relationship between this and an if-else or a switch case statement, then you're on the right track to understanding what step functions do. So good. I'm glad you guys can see that because, that should be popping out at you. And that's as complex as we need to get for step functions, because that's really just what you need to understand. That x, the coefficient of x, can be a dynamic value based on x, just as you would with with a series of if else statements. Okay? And now we're going to talk about the third method that the authors present for nonlinear data. And those are splines. So again, I'm pulling this straight from the book, but you should be seeing the notion of splines should come at you pretty quickly, right? Because they're kind of helping you with the different lines that they're drawing. They're telling you that you can also choose to have different points in your data, in that path through your ground truths, where you kind of make these turns, these splines, right? So here in this first one, you can see that not only is this line have a couple of splines, but there is a significant spline at the 50 value for x, where the pattern completely changes. Or down here, this is an exaggerated example of a spline where up to 50 there's a line, and then after 50 there's also another line. So you can have like these inflection points along your path that lead to a better model. Because again, all we're doing is reducing errors, right? You're reducing the distance between your ground truths and your model that you want to use as a predictor. So this is telling you that after 50, you are better off using these lines because they will lead to fewer errors than the line you were than the pattern you were using prior to the 50 value, but when x is less than 50. Sorry guys, I apologize. That came out of nowhere. I think I'm getting allergies or something. So when you're thinking about a spline, you should be thinking about these lines that have these inflection points at various times, because there's something significant. Excuse me, everybody. There's something significant that's happening at those splines that will reduce your errors if you take a different path at that point. That's basically what you're doing. Sorry, guys. That's basically what you're doing in a spline approach. Okay? So the authors, excuse me, and this is a secondary explanation of splines. Here you can see that there's more than one significant value, right? So here they're saying at the 25 value for x, at the 40 value for x, and at the 60 value for x, you need to add splines because everything below that or everything prior to that was not as effective. Okay? So, pulling from the authors, each change in that spline, it's called a knot. But then the question is, how do you know where to place the knots? Right? You kind of have to determine that. Or how does the algorithm, the formula know that? Right? So, again, just to reiterate, with splines, you're saying that you could have these different inflection points known as knots, right? I call them inflection points, but I should say knots. And those knots are where the pattern changes. Where you're going to say, well, no, when x reaches this value, I need you to do this instead. As is illustrated here, right? So here we can say that this model has 3 different knots. There's a not at the 25 value for x, there's a not at the 40 value for x, and there's a not at the 60 value for x. And all of that is determined by the pattern, the path through the ground truths that minimize your errors. May not be like an error-free path, but it's the path that minimizes your errors. Remember, we're always minimizing our errors, right? We're always wanting to make those metrics as small as possible. So, degrees of freedom is an effective way to find the number of knots that you need. So here, we'll just focus on this chart here over on the left side, the red chart. So here, we're saying that the mean squared error changes according to the number of knots that you have. So this is what the error is at 1 knot, right? Which is not great. In other words, that's just one single path through the line, through the data points, right? And that's not saying it's a linear relationship. It could still be a parabola or something else. But it's just saying that if I do a parabola and nothing else, there are no knots, there are no changes to that path. That's your error. That's your mean squared error, your MSE, which we've looked at before. But what if we allow 2 knots? Well, now we're getting an improvement because now that's saying that the data is broken up far enough where you can have a second pattern that fits the overall data better. Well, what about 3 knots? Well, now this is telling you, okay, yeah, you get even better. Well, what about 4 knots? Not a whole lot of an improvement. Well, what about 5 knots, 6 knots, 7 knots? You kind of keep on going, right? You kind of keep on going to figure out what exactly the pattern of that line looks like. Some of it might be straight. There might be points where you have a linear relationship, and others might be more curved, right? Like if we go back to that chart, right? Look at everything below 25. That's a linear relationship, right? Look at that red line. That's completely linear. But it's not after 25, right? After 25, it takes more of a curve. And then after 40 and 60, that's pretty flat, right? And then at 60, you kind of have a downward curve. So looking at the degrees of freedom helps you understand how many knots you should have, how many of those points happen for all of your data. Okay? Let me take a quick look here. Okay. So again, if we know that the degrees of freedom helps us figure out the number of knots that we can have, is there a danger here? Do you guys see any problems with this approach? I mean, it's good for us to want to go through our pattern, our data, and find the best possible pattern, right? But is there a danger here? Are there any risks that we run here? Give you guys some time to think about that. Rahul says, how to know that we are not overfitting when using more knots? Okay, anybody else or anybody agree with Rahul or anything else? Any other thoughts? What do you guys think? Um, Leo says, went for a call. Amrapali, good to see you. We are trying to overfit. Okay. Anybody else? Last call for answers? Okay, so Amrampali and Rahul basically have hit it on the head, right? That there is definitely a danger of overfitting here. Because remember, this is all testing data, right? This is all your training and testing data. But in the future, when you're making predictions, it's possible that you overfit the model to that data. And you definitely run that risk with the higher number of knots that you have. Because in theory, you could have 1,000,000 knots, right? And every single point would be like would have a change, right? Every single value of x would have its own cutoff points and its own values, right? Like you could literally draw like you'd end up with like a really funny zigzag line, right? But you could do that. You could have a knot at every value of x and then have this model that, lowers your error rate. But it might not do so well in future iterations, right? The overfitting is definitely a danger there, right? So that's something that you kind of need to consider in the future, where you kind of have to take the lowest number of knots that still give you a relatively good result. So here you can see that at the value of 3, everything else after that is kind of like, not a significant change, right? So you kind of want to use 3 because anything else above this is not a significant change, but you're increasing the risk of overfitting. Because the more knots, the more zigzaggy, the more perfect that line becomes. So that is definitely one of the dangers here. Let me go to the next slide because I do point that out. So so this is why smoothing splines exist. Right? This is where in the book the authors make the transition to smoothing splines. Smoothing splines, excuse me. If you just continue to use splines and knots, then you run the risk of overfitting the model. You can just use as many knots as you want, right? Just go to the previous chart and then just pick the maximum at like 8 and say, well, I'm just going to have 8 knots, right? But the smoothing splines help you control that because they're going to find you the best path to minimize the error metric, and it has a lambda hyperparameter that you can use to test with. Because the lambda kind of helps you temper those knots and helps smooth out the line in between those knots. And by smoothing out the line, you're potentially improving your error metrics. And again, it's always good to have hyperparameters, right? Because we're always looking, as I said earlier, the levers to pull, right? You always want to have levers to pull because as long as you have levers to pull, you have experiments to run, right? So this here is an example of a smooth spline with the previous data that we were looking at before, your age and your wage, right? So we went from this, which was using 3 knots, to a smooth spline that looks like this. And this is after tuning, after your hyperparameters and all that. So you can do as much work as you want with splines. There's nothing wrong with that. But the smoothing splines are almost like a check for yourself to make sure that you're not overfitting the model. Okay, super important to remember that. All right. Rahul says, also, can you please clarify why we're using MSC? I mean, we could easily repeat the same AI CBSE and may show different best number of not. Yeah, that's totally fine. You could totally do that. They're probably not going to be as divergent as you think they are, right? They'll probably be closer than you think they are. But yeah, if you want to use AIC or BIC, you can certainly do that. Or whatever other metric you want. The authors are just choosing to use MSC. I mean, these are not my charts. I'm pulling these from the books, right? The authors choose to focus on MSC. I'm on board with that. I understand the rationale for it. I use it quite a bit too. But sure, you can use other metrics. Okay. So I feel like I've thrown a lot at you guys in the last 20 minutes here. And that's okay. It's totally okay for you to be a little bit lost now, because I think that encourages you to kind of take a step back and be able to go and think about these things, right? Do your work on your own. Do research on your own. Go read the book on your own. That's very healthy for you to do, right? But I'm just helping you understand that there's multiple paths through your data. And that's ultimately what you're trying to do, right? What is the path through my data that helps me minimize my errors? And notice that I'm saying path. I'm choosing that specifically. I'm not saying line, because not everything's a linear relationship, right? We established that at the beginning, right? So keep that in mind, okay? Rahul says, I meant what is more practical in a job role, MSc or something else? I don't think there's a better best for this. It's to some degree, you just want to make sure you're using a valid approach, and you also want to be consistent with what you're using, right? Don't use MSc early in your testing and then switch to AIC later on, right? As long as you're consistent with what you're choosing, that's really all that matters. Don't overthink it, Rahul. Just choose something and use it as your baseline. At the end of the day, it's just a number, right? It's just a number that you're using, that you're comparing against. Did I do better or did I do worse? And whether that number is MSc or AIC or whatever, who cares, right? Did I do better or did I do worse? As long as you're consistent with what you're choosing across experiments, then it's just a number. It's just a value to compare against, okay? So the authors close the chapter by talking about local regression and generalized additive models, or GAMs. So here is where I'm going to divert from the authors, because my real world experience has taught me that if you can't get to an answer with these methods, to a reasonable model with these methods, then you probably have another kind of problem on your hands. It's likely that it's not a regression model, right? You kind of have to, because remember, regression models is still just one family of models. There's others, right? There's plenty others to choose from, and we'll talk more about this in the coming weeks, right? But that's why I've kind of put local regression and generalized additive models out of scope. Because if you've done all of these, right? You've done linear, you've done polynomial, you've done your step, you've done your splines. Like, what other signs do you need that you need to move on, right? Like in the workplace at that point, your boss is going to be telling you, okay, stop regression, let's do something else, right? Like you don't need to keep on beating on that same problem if you're just seeing, very small or no changes to your baseline model, right? So that's why I'm going to kind of put those to the side. You're welcome to read them, on your own time. But, I've never really used these because, again, by the time that you get to this, you've already tried, 4 different regression approaches? And if you haven't improved, then hey, it's time for you as a researcher to use your own reasoning and say, okay, well, maybe regression is not valid here. That's totally okay to reach that conclusion after, after you've documented and run those experiments, right? So again, you're welcome to read that. Obviously they still present some good info in there, but my real world perspective is that they kind of fall out of the scope for the session that I want to run today. All right. Okay, so I believe that after this, we are ready for going into our coding, right? So as the same as before, what are we optimizing for? And again, Rahul, coming to your previous question, right? That's one of the reasons why I always put that at the very top of the framework example, right? Because I want to be consistent in what we're comparing. So what are we optimizing for? What error metric are we choosing, basically, right? Sorry, guys. I must be getting allergies or something. Some dust must be in the air. Ugh. Second part is, what does the code look like for all of this, right? We're going to be code editors, not code writers, right? Because we're preparing for the future here, right? AI is part of our future. So we're going to actively choose to use ChatGPT or other AI tools to help us write the code. Okay? And we're going to be working with a couple of examples, right? In our lab. Professional level development environment, appropriate data set, and then we're going to use polynomial regression. If we have time, we'll go to ridge regression. Because another thing I want to do is I want to do a lot of plotting. And personally, I'll be honest with you guys, plotting is not one of my strengths. I know Matplotlib just a little bit, just enough to be dangerous, but not a lot. I'm happy to call myself terrible at it. I've never been a big plots guy. I'm more about, outputting and looking at, different portions of my data, portions of my data frame. I'm really big on outputting to the console and kind of reading it from there. I'm more of a reading guy than I am a visual guy. So we're going to do some plotting, right? And I might make some mistakes, and I'm just not really good at it, right? But let's try it, right? Obviously, we've had a very visual chapter, okay? All right, so like I said, I feel like I've thrown a lot at you guys in the last 20 minutes. Does anybody have any questions or any doubts they want to clear up before we move on to the coding portion? It's possible that we might just do polynomial just because, I feel like it's been a little bit of a heavy session. But let me know what you guys think. Are you guys okay? Are you guys on board? Any questions? Give me some feedback here. I'll give you guys a minute or so to think about that. All right, Patrick says that he's on board. Don't be embarrassed. It's totally okay to say you're lost in a couple things. If I can clarify some things, I will try, or otherwise we can take it to the Discord after the class. But anybody else agreeing with Patrick? You guys on board? Did I lose you guys? Are you guys asleep? I'll concede this isn't exciting stuff, but this is part of the data science work, right? For right now, we're still going through the class. Feel free to ask me that question later, but let me just focus on wrapping up the class here, okay? But welcome. Rahul says, I'm on board as well. In fact, I am finding it interesting, have so many questions. Yeah, I think it's an interesting chapter too, right? Because again, it's just pattern matching, just helping us kind of see where different data points lie, right? Amram Pali says, all good, okay. Anybody agree with Amram Pali? You know, last week, people took some of that work, like Yassine, and then he posted on Discord and said, hey, I was thinking about Sunday's class and here's what I came up with. You guys are also welcome to do that, right? You guys are also welcome to say, okay, I might not participate in the chat today, but I might post something in the Discord later on this week or whatnot. That's totally okay. All right, so I'm going to keep an eye on the chat in case anybody else wants to raise their hand and say, that they're good or they're not. But let's go ahead and start looking at some of the coding side of this. So as before, okay, my note says I'm on board as well. Okay, cool. So as before, we're going to be using Visual Studio Code. I created a file for some plots already because let's ease into this. Let's create some plots because again, I'm emphasizing how much pattern matching there is, right? So let's do some plots, okay? So let's ask ChatGPT to help us, right? Because remember, we are code editors, not code writers. Let me know if you need anything up, blown up on the screen, guys, okay? I think I'm using a reasonable font and all that, but let me know. Okay, so this is the first prompt I'm going to use. And ChatGPT is recognizing that we want y equals x squared. So let's carry that over. It'll be bigger in here. I think this is reasonable code, right? I mean, it looks perfectly reasonable. So we're going to go ahead and save that. And we're going to bring up the terminal window. That should be big enough. Let me know if it's not. We're going to check to make sure our file is there. We're in the right directory. Okay, we are... I'm typing wrong. What's going on here? It's not recognizing my command of ls? That is weird. Okay, my terminal has gone bad on me for some reason. All right, guys, let me restart terminal. Terminal's acting up. Give me just a second here. Is left. Okay, that's weird. I don't know why it was acting up like. All right, so let me make that bigger for you guys. Yep, so we are indeed in the right directory. I'm going to activate my environment. Okay, so now I can go Python plots.i. And it opened this. What do you guys think? Did ChatGPT do a good job here? Okay, Lakshmi also says it's going good. Okay, good. Good. Glad to see you guys are still on board. It gets a little harder here, guys. I get it, right? But you know, all of you are smart people. You'll get it. You'll get it. What do you guys think? Did ChatGPT do a good job here? Patrick says looks good to me. Okay. Anybody agree with Patrick? Nobody else? But yeah, I mean, I agree. I agree with Patrick. Right? This is a perfectly reasonable result for x squared. We know that x squared should be a parabola, and you know, ChatGPT chose a reasonable range of -10 to +10. So yeah, this is a pretty good plot for x squared, right? So we're going to close that out. We're going to go back to our code. We have an x squared plot now here in our directory because we asked it to save to the local working directory. What does x cubed look like? So I'm seeing that this is where the formula is being created, right? Because again, we're editing the code, not writing it, and we can go ahead and save this as x cubed. Yep. Go back to terminal, run the same code. And that's what it gave us. Does that look right to anybody? Hey, Venus, good to see you. Venus, I see that you're on Instagram. Feel free to switch over to YouTube to get a widescreen view. Okay, might be easier to understand some of the charts and code that we're doing. So this looks terrible, right? We obviously made a mistake somewhere, and I think I know where. I was too quick to rush through the editing, and I should have made the additional change up here, right? Because here is where we're setting the value of y, right? So that's my mistake. I'm going to save that. Patrick says, lol, not looking too good. Yeah, you're right, Patrick. I made a mistake. It should be shaped, I guess. Okay, Lakshmi. So what about this? Are you on board with that, Lakshmi? Or anybody else? Anybody else on board with this one? This is x cubed. What do you guys think of this one? Lakshmi says this looks good. Yeah, I agree. This is a much more reasonable value for y equals x cubed, right? Yeah, Patrick says gorgeous. Yeah. This is pretty good, right? Anybody want to go to the fourth? I want to see what the fourth is, right? Go back to our code. Got that. Got that. Oh, whoops. Anybody want to tell me what the fourth looks like? What are we expecting here? What's the curve going to look like? Anybody? Yeah, I think I made all the right changes. Anybody want to guess what the fourth looks like? Okay. So Sarvesh says x to the fourth will look like x squared, but more flatter at x equals 0. Okay. All right. Well, here it is. Sarvesh, I really like the way you describe that, and I think that's the chart we got, right? Like a big bowl. So yeah, I think we got pretty good code here from ChatGPT in a matter of seconds, right? So now, let's take this. And give me a second here, guys. I'm going to bring up a previous. So, Patrick and Leo. I don't like to call on people, right? But I know that you guys were really big on this chart down here, right? What do you guys think now? What do you guys think? Maybe not x squared? Maybe x to the fourth? Would x to the fourth address more of these outliers or more of these like kind of like edges that I mentioned earlier? What do you guys think? Patrick says, yeah, maybe x to the fourth for sure. Yeah, Patrick, I agree. Right? Still maybe not a great model, but you're capturing a lot more of this noise down here, right? Because as Sarvesh pointed out, it has a flatter bottom. So now, all of a sudden, this feature comes back into play, right? Patrick says, I think it would still be as predictive as we, or I think you meant to say won't be as predictive as wanted to be. Though. Yeah, that's true, Patrick. But is it an improvement on your baseline? Because you started with a baseline of a parabola, right? You and Leo saw a parabola here, which is not wrong. There's clearly a parabola there, but maybe you need to flatten it out. Which is what x to the 4 does, right? Because now you're capturing more of the data down here, right? But here's the point: whether it's going to be your final model or not, that's not really the point. The point is it's a valid experiment, right? It's a valid experiment for you to say, okay, well, let me try this other polynomial. Totally okay to say that, right? That's part of the process. You don't know what the right polynomial should be. Now, we're building that skill, right? The reason I wanted us to go through these charts, through this plotting, is because these should almost be like little flashcards for you, right? Where you should be kind of playing with these plots. So in the future, when you do another scatter plot like Yassine did here, you'll be able to say, oh, wait a minute, I recognize that. That's x to the fifth, that's x to the third, right? You can say that, right? So just like I said, for me, this caught my eye here, right? This fits an x to the third, right? The x cubed. But you're only going to know that if you've plotted these ahead of time. I really wish the authors had taken more time to do those plots because, again, that's how I was taught. The book that I used had a whole series of plots that would help you with that. So I'm going through the plotting exercise because I want to encourage you to do the same. Get familiar with these plots, right? Get familiar with not just this, but what if we do x to the fourth and then we add a value of 5 or we subtract x, right? Like here, let's do that. Right? Oh, wait, let me go back. I gotta close this out. So what if we do this? What if we go ahead and say this is minus x? Let's go ahead and save that. Oh, and this is fourth minus x. We get a little bit of a change, right? Let me go to Visual Studio. Might be easier to see in Visual Studio. So that's our minus x. And that's our fourth. Is there a change? Kind of, sort of, right? It's kind of a small one. Because x to the fourth is like a big number, right? So reducing it by x is like almost like a negligible difference, right? But you wouldn't necessarily know that unless you did these experiments, unless you built up those patterns in your mind, right? So that's why I wanted to start here, to encourage you guys to do that type of experimentation, to build up those patterns in your mind. Super valuable for you to know this, right? So yeah, so I think that this, you guys are getting it in terms of like why you would want to do this. Because if you go back to the previous scatter plots, new ideas, new experiments start to come up, right? And you're never done with modeling as long as you have experiments to run, right? Because you'll never know until you run the experiments, right? So I think you guys are getting it. Super important to think about the plotting. So let's move on to the next portion, okay? So eventually I want us to do polynomial regression. But before we do that, we need to get some polynomial data, right? So let's start a new file. Polynomial data.py. And we're going to ask ChatGPT to produce some polynomial data for us. If you remember, we asked for data, I think, in our first class. So yeah. So let's ask in CSV format, I want the data points to fit y equals m. We're gonna declare the coefficient, right? We'll declare a coefficient of 42 because we already said 42 is our favorite number, right? 42x squared. And we'll use a low b. We'll use a b of 5. And we want to do this with a low MSE. right? We'll do a both low MSE and high MSE, okay? Also, I want to see the data points plotted on an x squared chart. What is the Python for all of this? Okay. Okay. So let me bring that over for you guys to see on Visual Studio Code. So remember, we kind of asked for two different things, right? We asked for to generate data, and then we're asking it to generate the plot, right? So I'm gonna just do a quick separator here, so we can talk about the code kind of in two separate sections, right? All right. So we're gonna focus on everything here above the line here. What do you guys think? Is that reasonable code? Are we gonna get some good data here? What do you guys think? Let me know. Oh, sorry, I took down Visual Studio Code. Anybody want to give their opinion on this code? Remember, just look at the top half, right? We're just going to focus on the data generation. Nobody, huh? Well, I'm going to go ahead and say that this code looks perfectly reasonable to me. We're going to get 100 data points. It's telling us the range for the X values that it's going to use, right? And then here, it's introducing the element of noise. And that's what ChatGPT is using to control how good or how bad the MSE should be, right? Because the lower that noise is, the closer the points will be to the line, right? Will be to the ground truths. Here, we're seeing our formula, which is what we wanted it to fit, right? We said y equals 42 times x squared plus 5, right? Which fits our pattern of y equals mx plus b. And then it's saving it to quadratic data. And then in addition to that, I asked it to plot. And these look like very reasonable numbers, or very reasonable code, rather. and it's going to save it to quadratic plot. And it's basically just using the same formula, right? Now, plot the original function without noise. Yeah, that makes sense. That makes sense. So where I was getting confused is I was getting confused between the scatter versus the plot. So the scatter is what's going to put out our actual data points, the red points. And the plot is where it's going to put out like the black line, right? The proposed model. So let's go ahead and illustrate this by actually running this. Let me go back to our terminal, make sure the file is there. And it is Python poly data.py. Okay. So it gave us that. What do you guys think of the plot? Look good, everybody? So the blue line, just so we're clear on this, the blue line represents our desired model fit. And the red line represents the different data points that ChatGPT made up, right? It made it up using NumPy, and it introduced some noise to give it some variance, right? But overall, this is a great model, right? Because our path through the data points is pretty good. There's very little variance, right? What do you guys think? Okay, Manoj says looks good. Okay. All right, I agree, Manoj. This looks pretty good. But I want to have two data sets, right? So let me go back to Visual Studio Code. And this looks like, so we got our quadratic data plot and we got our quadratic data. I want to make a change though. What if I do this? And I'm going to go ahead and make a change here. And then I want to make a change down here. So if you guys notice, just in case you missed it, I made an adjustment to the noise parameter. Amram Pali also says looks good. Okay, great. Thanks, Amram Pali. Okay, let's rerun this. Now remember, I made a change to the noise here, right? What are you guys expecting this chart to look like this time? Give me your speculation on what the chart should look like now that we made an adjustment to the noise value here. We made an adjustment to the noise value that NumPy is using, and then that value is being added down here, right, to our equation. What do you guys think? Now, what is our model gonna what is our chart gonna look like vis-a-vis the blue line? Give you guys a minute to think about that. Lakshmi says more outliers. Okay. Do you agree with Lakshmi? Do you want to give another perspective? Let me know. More data points, not too much overfitting, hopefully. Okay. That was Rahul's answer. All right. So here, this is what it looks like. So let me bring it up side by side. So that's what our first one gave us. And this is what our second one gave us. Are these reasonable results that ChatGPT gave us? Because remember, to some point, not only are we understanding what's going on, but we're also verifying that ChatGPT gave us good code, right? Because we didn't write this code, right? So what do you guys think? I'm going to say that the code is good. This chart here on the right is our low noise value, and on the left it's our high noise value. Manoj says a little high variance. Yeah, but we were expecting that, right, Manoj? Because remember, all we're doing right now is creating data, right? So we were kind of expecting that. Rahul says, I think this looks good. Patrick says, agreed. Yeah. But remember, we kind of want this, right? Because the next step is we're going to use these same data points and we're going to ask linear regression, or excuse me, regression overall, to help us find a valid model, right? See, what we're really trying to get to is we're trying to get to a point where we can use this data to have code that's going to come back to this equation, right? I want to get code that is going to that's going to tell us exactly this equation. Excuse me. So that's why, excuse me, sorry. That's why we need the two equations, the two data sets, right? Because one of them is going to fit that equation really well. Another one is maybe not, right? And in fact, just to kind of like really illustrate that, I want to go ahead and make a second set, make another set. Because I kind of want the difference to be a little bit more dramatic, you know? Okay. So now look at this. So now this data is fit to that same function, 42x squared plus y, plus 5. But look at how much more noise we've introduced. A lot more variance, right? So are we likely to be able to come up with a model when we switch over to the modeling side? Are we likely to come up with a model with a low MSE? Probably not, right? So let's do that, right? So we have two data sets to work with, right? Let's go back to Visual Studio. We have our quadratic data, which produced the first chart. And then we have our quadratic data with a high excuse me, I meant to, yeah. That's going to have a high RSE, which is also in turn going to give us a high MSE, right? So we should be expecting two completely different results when we go to model these. Because remember, we know what the answer is ahead of time, right? Because we needed that to do the model to create the data. But now we want to test if the code can come up with that same answer, the y equals 42x squared plus 5. That's kind of what we're going after here. So let's go back to ChatGPT. We know that it can do regression via scikit-learn, right? So we're going to go ahead and do that because we know that from the previous classes, right? So please scikit-learn for a regression model data. So the MSC, and all of the code values. All right, so let's see what this comes up with. Okay, good. All right. So I love that. I gotta start a new file. Now this is modeling. So I love that ChatGPT is keeping the context and it knows that it named our file quadratic data, which is great, right? And we have X and Y as desired, right? So now we're going to see what this model gives us. In theory, we should be expecting that it's going to tell us that the coefficient is 42 because we know that we use that, right? And that the intercept is 5 because we know that we use that, right? That's how we created the data, right? That's kind of how we're walking backwards towards a viable piece of code, right? Now, I have to say that I'm a little bit concerned that it specifically imported linear regression as the model. I don't know if that also encompasses polynomial regression. I'm not intimately familiar with scikit-learn to know whether that's encompassed in one or if that's a different one. But we're about to find out, right? So let's see what happens here. I'm expecting that it's probably going to try to fit a linear line, and we know that our data is not linear, right? We saw the scatter plot. We know that it's not linear. We know that it's a parabola. So let's try this. I'm not anticipating good results if it uses linear regression in a strict definition. So this is called regression modeling. So let's see what it tells us. Yep, there it is. So Python regression modeling.py. Okay. What do you guys think? Here's the MSC, and here's the intercept, and it gave us a coefficient of 0.1212. Is anybody happy with this MSC value? Do we want a big MSC or a low MSC? K and Kush, welcome. Patrick says it ended up fitting a line. Yeah. Yeah. Yeah, so my initial read of the code basically showed it's going to be a linear regression, right? Patrick says that is bad MSC, it is too big. Yeah. Yeah, so from our previous study, or if you read the book on your own, you should know that MSC, you want it to be as low as possible, right? Because MSC is a value of how far you are away from how far your model is away from the ground truths, right? So yeah, this is a terrible model, right? And it's because it's using linear regression and not polynomial regression. So we didn't guide ChatGPT in an appropriate way, right? So let me go back and let's get a new prompt going, right? Oh, that's funny. They're doing A/B testing on ChatGPT. I've never seen this before. Okay, but you can see here that it's now asking for a polynomial features. Actually, let me bring this over to VS Code. Let me see which one's better. sklearn pre-processed polynomial feature. I think it's the same code. It's just the response that's different. So let me just bring over one of these. Okay. So it's still loading the data, X and Y, polynomial features, and then it's going to fit a transform on X, right? Because we know that X is our independent variable. It's still going to use the linear regression library, but it knows that there could be a polynomial value in X, right? And it's going to try to fit the model, and it's going to give us the same coefficients, intercepts, and MSE as the outputs. So from what I know of scikit-learn, this looks like pretty reasonable code. So let's go back and run it. Okay, what do you guys think of this one? A couple things are jumping out at me. Excuse me, let me go back to VS Code. Remember this formula, right? This is what we use to generate the data. 42 times x squared plus 5. Are you guys seeing that anywhere here? What do you guys think of this result? That's right, Patrick. Yep. We got pretty good coefficients, right? Look, we got exactly to the 42. We got 4200. The intercept could use some work, right? 4.5. And look at our MSC now. Our MSC is much better. Patrick says, let's say correct within noise. Yeah. Within noise, and remember, and our N is only 100, right? 100 points is kind of hard to model on. So yeah, it got to a very reasonable number. The modeling worked, right? We got to the coefficient. We got to almost to the intercept, right? We can improve on that. And we significantly lowered our MSE. So I like this code. This code is pretty reasonable. This code can get us to a polynomial answer. Michael says it looks better. Yeah, you're right, Michael. It looks a lot better. Prashant says, can I get the full course? Yeah, Prashant, go ahead and go to my YouTube, Data Science with Dennis. All of my live streams are saved up there, and you can view the course, okay? But yeah, guys, I'm on board with this. This is a much improved model, right? So now, so what we've shown here is we've shown that ChatGPT gave us reasonable code for us to use this for polynomials in the future, right? So now let's do one final test. Because here we're using, oh wait, did I run the wrong file? What file? I ran regression modeling. Okay, yeah. And yeah, I don't know why I switched that. Yeah. Yeah, okay. So here, remember that we also have a second quadratic data file, right? And that is our high RSC, right? So in this point, we're not going to change the modeling, right? We're not going to change the modeling code, but we know that we have another file that has a lot more noise, right? So now, are we optimistic that this same code is going to get us to the same coefficients? Probably not, right? And here's the results. Instead of 42, it got to 40.8. And instead of 5, it got to minus 75. And look at the MSE. The MSE is better than our baseline, right? Because before we were like, what, 1.6 million? So our MSE is better, but we're not really close to the model, right? The coefficient is approaching the right answer, but the intercept is terrible, right? So same code, same polynomial problem, but we know that one set of data fits the model better, the other set of data, kind of sort of fits the model. And here we've proven that ChatGPT picks up on that, right? Or the code from ChatGPT picks up on that. But with this model here, we're basically at a point where we can have a positive expectation that the code that ChatGPT gave us, given different data and all that, is going to give us something that we can work with. Okay? I think that's coming across clear. Let me know if it's not. Okay, guys. So I always like to leave you guys with some further testing, right? So can you take the same approach and can you create code for a smooth spline model? We've already determined why we wanted to do smooth splining, right? Because that way we don't let the splines get out of control and overfit the model, right? And remember that smooth splines also give you the lambda hypertuning parameter. That's important. So can you take the same knowledge from today and create a smooth spline model? I'll leave that with you guys for the self-study. We've covered a lot today, guys. And if you feel like the level of difficulty has increased, it has. But this is where the work of a data scientist is, right? The type of experimentation, the type of comparing of graphs and plotting data and things along those lines, that's the work of a data scientist. That's what you do on a day-to-day basis, right? And I think that you can see how we're doing all of that in partnership with ChatGPT, with AI tools to help us, right? So I hope that's coming across. I think it's coming across based on the feedback that all of you are giving me. But take some time to kind of reflect. Take this information in. I know we covered a lot, right? But this stuff's important. And also realize that you're building a lot of really good fundamental building blocks. Because remember what I told you? That all of data science is what are the features and how much weight do you want to assign to those features? We're still doing the same thing. We're just determining the better path, and we're acknowledging that the world is not linear. Those paths may not necessarily be linear, right? Lakshmi says, thank you for today's class. Yeah, Michael, things good. I'm glad you guys are still with me. We covered a lot, right? Join the Discord, ask questions in there, do follow-ups. Hey, you can make a post. Hey, I did my smooth spline model. Here's the code ChatGPT gave me. What do you guys think? Get some of that conversation going, okay? But I really appreciate the time we spent. I really appreciate all of you that stayed the whole time, and we're at 2.5 hours. You guys are amazing. So thank you so much for that. Take care of yourselves, take care of your families, and I'll see you next time.